So this is the Unit 6 review, just kind of refreshing everything that we've gone over this unit here. We did the intro lab, of course, with the tape top, the tape bottom, the foil, and the paper. The main point of this was if you have a top piece of tape with a bunch of atoms in it here, that top piece of tape will, when it's neutral, have three electrons in it. When it changes over to a positive charged piece of tape, it's going to lose some of those electrons. So now these atoms will only have 2 electrons. Remember, electrons are negative, and so if you lose a negative, you're actually becoming more positive. So that was for the top tape. Some assumptions that we made when we did this: we're assigning positive charge to the top tape. That we could later prove through the series of types of material. The reason why the top tape was a positive because it was the resin, whereas the bottom tape was a plastic. So that was the triboelectric effect, where there's this order or series in which determines a positive or negative charge. For example, your hair becomes staticky all the time because it's naturally positively charged. We did the bell work question here, converting grams to moles. That won't be on this test. Conductivity of materials lab. So we use the conductivity tester to figure out if we had an insulator versus a conductor, which I believe is on one of the next few slides here. We talked about sticky tape here again. So this is a neutral example of sticky tape, where this is also a neutral example of tape. When the top piece was attached to the bottom piece and then torn apart, we get the top piece being positive, bottom being negative. One of these electrons is essentially jumping down into the atoms below it, causing a charge differential. So these are the neutral homogeneous atoms. We had this polarization effect within the atoms. So if this was a piece of aluminum foil here, and this was that plastic wand that we used, when you brought it near it, the charges all moved towards that positive charge. All the electrons, being these negatives, moved towards that positive charge. As a result, there's a certain attraction here between these two materials, and the aluminum foil swings out towards that plastic wand. So polarization here can also occur like this, where each atom individually becomes polarized. The charges move to the side of the atom, and this is the case of an insulator. So an insulator versus, this would be a conductor. So something that can conduct electricity, the electrons can flow all the way across the material, like an aluminum foil, whereas in the case of like paper is an insulator, and so as a result, these charges will stay inside of their atoms, respectively. Now the paper is still slightly attracted to it, and that's because they all do shift in their atoms towards that charge. So that's how we define the difference here. Again, this would be the conductor, because the electrons can jump, where this is the insulator, where the electrons don't leave their atoms. We mentioned the discussion of electrolytes. Electrolytes are basically the ones that can conduct electricity. Things like sodium is a great conductor. Chlorine is a conductor. It's an ion. It's an electrolyte. Non-electrolytes are things like sugar. They resist the flow of electricity. So sugar is C6H12O6, and that's this really big particle. It's formed in the shape of a ring. It looks something like that. And each of these points is an atom, and has a couple of atoms attached to it as well. So this is a very big particle, non-electrolytes. That molecule stays together in solution, so that resists the flow of electricity. Whereas something like salt, these two parts will break apart in water, and then they can transfer electricity throughout that material. So these are generally made of ionic compounds. They are a metal and a non-metal. They range in their strength, and there's some strong electrolytes and some weak electrolytes. Some materials are better than others. Non-electrolytes, again, are that molecular compound, usually between 2 or more, and this is the important part, non-metals. So that's why when we got to the naming, these were molecular and these were ionic compounds. The worksheet 1 took a quiz. In the mercury simulation, let's see, account for differences in the melting and boiling points of the 3 types of structures. Ionic bonding is generally the strongest. Remember, they have that lattice structure where you might have a central atom, but it's attached to multiple atoms around it. And then there's one kind of back behind the board here attached, and one coming out from the board as well. So this central atom here, I'll highlight that in red, is actually attached to 6 different blue ones. So if the red is sodium, the blue then is the chlorine. There's a lot of interaction going on, and that's how we define that lattice structure. Metallic bonding is very high also. That also has that lattice structure, if you remember seeing those images. The molecular bonding is weaker. It's generally like hydrogen bonds, that's in water, for example. And then the weakest, of course, is the atom to atom or molecule to molecule. So gases, oxygen gas. So an oxygen molecule bonded to another oxygen molecule, they have very little attraction to another set of oxygen molecules. So this is O2, this is O2 here. This attraction is very weak. That's why it's normally a gas. Predict which of these substances would conduct electricity when molten. This was a question from one of the worksheets. The ionic ones, the charges can move, and metallic ones, electrons can move. That goes back to the conductor that I talked earlier about. Any of these conduct electricity as a solid, only metals in the solid state. Last thing here, talking about molecular compounds. Molecular compounds are nonmetals bonded to another nonmetal. These generally have a lower melting and boiling point. They do not conduct electricity, as we've said, and they, in the simplest form, they're a single molecule. So again, if we break the periodic table down into its constituent parts here, I'm going to try to draw this as best I can. If you look on the periodic table, there is kind of a stair step here that goes something like this down to the bottom. And everything over here is non-metals. And so that might be something you want to add to your periodic table to help you remember that. Everything to the left, then, in the green over here, these are all metals. So remember, in the naming system of this, charges do not balance. And we use those prefixes to enter those. Whereas conversely, with the ionic ones, you have to balance the charges. I think that's about it for the review for these.